Alright, let's talk about thin layer and column chromatography. This is perhaps the most efficient way and the most utilized way of separating and purifying organic components from one another. And technically what you're doing in chromatography is to run a solution of your mixture. So technically you have these plates, we call this the thin layer chromatography plates, and you place your mixture at the very bottom. Now that plate is in direct physical contact with a solvent. That could be a mixture of different kinds of solvents, or it could be just a regular solvent, period. But what happens is that the plate starts accepting and absorbing that solvent via capillary action. And it does so until it basically reaches the top of the capillary. Now in the process, what ends up happening is that you get that mixture to kind of go along with the solvent for the ride, and you start kind of taking into consideration the intermolecular forces of interaction of your mixture towards the solvent that is traveling up this TLC plate, and the intermolecular forces of attraction between your solute and the plate itself. So we're going to talk about that in here. All right, so technically speaking, although this can actually be modified and changed at will so that you can change the polarity of the TLC plate, the most traditional and common ones are TLC plates that have this silica um, surface. And the silica, from time to time, in different silicon atoms, will have the hydroxyl functionality present. So you actually have uh, polar segments present in your TLC plate. And what you end up doing is you're mixing this stuff with a solvent that is non-polar. So you have this, back and forth, are you having your molecule react with a polar substance, or you have it react with a non-polar substance? And the answer depends on what kind of molecule it is that you're separating. The ones that happen to be more polar are going to try to spend their time interacting mostly with the polar surface. But molecules that are mostly nonpolar will do the opposite. They will interact the least with the surface, and they will interact the most with the solvent. And what that basically means is that when you start with a mixture and you have the solvent traveling up the plate, you start separating some of these components. And ultimately, if you do this long enough, you can have a very clear separation. You can see different spots at different distances, counting from the bottom of the plate where the marks were originally placed. And simply put, your solvent being nonpolar, if the spot is closest to the end, the solvent end, then you basically have a nonpolar substance, a nonpolar solute present in this mixture. On the other hand, if the spot remains very close to the original place where you input the mixture, then what that's telling you is that this particular fragment has to be more polar, and is the most polar out of everything here because it remains closest to the original spot where it was located, and that can only happen if the interaction is strongest between the plate and the substance. All right, now what we end up doing with this is taking a look at a ratio. In particular, we measure the distance traveled by the solvent front and the particulates that we're separating. And we always do it from the point of view of the original distance in which these mixtures were located, right? So this is our 0 centimeter or 0 millimeter mark. And we basically look at how far up we have gone here. And what we end up doing is we take the distance of the substance and we divide it by the distance of the solvent. And this results in something we call the RF values. The closer the values to 1, the more nonpolar your substance is going to be. The closer your value is to 0, the more polar your substance is going to be. And mind you, this is for the traditional setup. If you change the overall feature of your TLC plates so that they are nonpolar and you use polar solvents, then the opposite trend will appear. But here solvent is nonpolar, plate is polar. Okay, so the distance of the solute divided by the distance of the solvent. The good thing about these RF values is that technically speaking, it doesn't really matter where you stop with the solvent. In some cases, obviously, it will be more difficult for you to do the calculation because these things might be too close together. But you can measure the distance travel for the solvent. And if you look at this ruler, this looks roughly a little bit above 4.5 centimeters. Looking at the blue line, we're a little bit below 4, about 3.55 to, kind of approximate. So 3.55 divided by 4.5, which is what we're estimating for the solvent front, is a value of 0.8. For the red dot, we are roughly around 1.7, right? And that's kind of what we have right here. 1.7 divided by 4.5, which is the distance of the solvent front, that's 0.4. And a similar measurement for the black line right here, or the black spot, we are about 0.7, 0.8, yeah, 0.75. That's what I selected. And that's divided by 4.5, giving you an RF value of 0.16. If you let this go a little bit longer so that you are very close to the end of the plate, and this is usually what you want to do experimentally because this will give you the best separation and the most conclusive results. But technically speaking, in theory, if you look at the distance traveled, in the case of the blue spot, about 6.8 centimeters, the solvent is about 8.4, this is 0.8, same value that we got before. The red spot is about 3.3 distance travel, 8.4 for the solvent, 0.4, and then your RF value for the black spot is about 0.16, which is the same thing as before. So theoretically speaking, those ratios are not going to change irrespective of where you stop with the solvent front. But experimentally, you want this to be kind of close to the end of the plate so that you have the best separation between your spots. So this separation is just a lot. And if you select your solvent conditions just right, you can actually separate most any organic substance from any other contaminants that may be present. Or perhaps you have a mixture of different products after you do a reaction and you do want to collect both products. Well, this will allow you to separate them both from each other, collect them, and then you can analyze them as you normally would. And their RF value, by the way, it's definitely um, a representation of the molecule itself. So knowing the RF value is a means of you identifying the molecule. This, of course, means that you have to have prior knowledge of what the RF value of a pure substance is, because without that information, then you won't be able to tell what's what. Okay, well, that's it for this entire lecture. I know it's a lot of information, and hopefully most of it made sense, but if not, don't feel shy about reaching out to me, asking questions. This particular lecture I like a lot because it tends to show you what we do in the laboratory to some extent and the type of techniques that we utilize to make sense of how to purify substances in the organic chemistry realm. Okay, without anything else to say, I will stop the video here and I will see you on the next one. Bye bye.